This is my first SciPy conference. Thank you. Thank you. And today I'm talking about my personal project that is simultaneously demodulating FM broadcast radio. So yeah, let's get started. Who here already know what SDR is? Please raise your hand. Oh, okay. So SDR is basically a USB stick that will receive radio waves from a couple of megahertz to all the way up to 5 gigahertz or something, depends on the hardware. And what it does is to digitize these electromagnetic waves into a digital signal that you can process later on. It's different than normal radios, traditional ones, because it does most of the digital signal processing internally with FPGAs and on your computer using DSP. So it's quite useful. You can do a lot of things with it. For example, receive digital television. Here in the US is DVB and DVB-S2 from satellites. Also LTE, 5G networks, and even Wi-Fi signals. And FM broadcast is like the old transmission protocol for radios. It uses frequency modulation to transmit encode information on a carrier wave that is varying in frequency. So whenever you tune to a FM radio station, you are receiving a carrier wave that encoded audio signal that we hear after the demodulation of the radio. And this encoded information can be recovered by using a differentiator and also an envelope detector after, and then we play on the speakers. And turns out this is quite easily to be done with vanilla Numpy and SciPy Signal functions. For example, here we have the demodulation of FM using just Numpy and SciPy for decimation. So first we take an angle of the IQ signal that comes out of the SDR. Then we will unwrap that and then run the differentiation. And after we just divide by P, and then we have our envelope detection. And later we just decimate the output signal to match what our sound card will receive to play. And that's the mono audio. For stereo audio, we need to do further DSP to complete things. So yeah, this is vanilla SciPy and Numpy. You can try that with a cheap RTL SDR. There are multiple tutorials on the internet, and it's very cool to do this kind of stuff in real time and see everything working together and you receiving something in real time. So this is actual signal from FM radio. So here we can see the carrier wave varying in frequency, and that's this variation in frequency is the actual sound that the FM radio is transmitting. And it's not transmitting just sound, it also transmits digital signal like the RDS signal that you all see on your cars, that is what music is playing and other information metadata of the music. So what happens when you attach the SDR with the SciPy and Numpy here? So this is the radio core project, my project that I wrote, that will receive like 20 megahertz of all the bandwidth available for FM radios in the US and all over the world, and receive that in real time, the entire band. So what you are doing is receiving all the FM broadcast stations at the same time. So it's cool because you can then channelize the input into individual FM stations by 200 kilohertz. That is the bandwidth of each channel. And then you can demodulate the FM broadcast and into a stereo audio and play that simultaneously, or just store the audio on your disk. Or if you are feeling lucky, you can also use like NVIDIA automatic speech recognition to analyze all the FM radios in a real-time fashion. And it's cool because all the data is already in the GPU, so you don't need to ping-pong the data back and forth from the CPU to the GPU using this method. The radio card works by just defining this struct here. That is all the configuration that you need to run radio card. It's if you want or not to use CUDA, because it can happen if you are not on a NVIDIA or AMD enabled machine, you can disable that and run just on the CPU, but the throughput will be now impacted here. And also the input rate that will vary with your SDR. If you have a high-end SDR, you can receive the 20 megahertz at the same time. If you have an RTL SDR, that is a cheaper SDR, you can lower this number down to like 2.5 or something. The device name, that is the device you are using, and also the de-emphasis. That is a process that FM broadcast radios use to improve the audio that is transmitting throughout the medium that is the air. So they use this DSP processing to improve the audio that is transmitted. And in the US, the Americas and Korea is 75 minus 6, and the rest of the world is 50.6. So you need to change that accordingly depending on where you are. And the cool part is the channels. So supposedly we have a 96.9 megahertz channel, and this channel is a FM broadcast. So we put 240 kilohertz. And also the output sample rate that is 48. This is generally 48, but some audio cards will need to lower this to 32 or something. And finally, which demodulator do you want to use? So wideband FM, the WB-FM, is the demodulator that will output a stereo signal, and also has the mono and just the FM for like ham stations and stuff, if you want to do that. So it's array. You can put as many channels that you want here and choose your demodulator, or just write your own demodulator here. So the good stuff about so I'm now talking about what I learned here on this project and how to make a real-time application work better with Python. A real-time application depends on fast processing and also no time to process more than it's. So the data is being generated and consumed at the same time, so you can't have hiccups. You need to process the data smoothly, otherwise you have some clipping or audio effects. The first thing to improve your optimization or your excuse me. So the first thing to look at is the floating point precision, because the wrong floating point precision can generate inefficiencies on your code. So for example, you don't need a cannon if you want like a BB gun or something. And this will impact your memory usage and processing performance if you choose the wrong floating point. For example, if you are counting to 1 to 10 in increments of one single, you don't need a float, but you can use like float 32 instead of float 64. That is way more precise, and we'll use double the memory, and we will use the number of the processing power. And also be mindful of the D type of your array, because sometimes it will be created implicitly, explicitly, and everything will be float 64 and while you don't need it. If you use it, this write is really free real estate. Sometimes third-party functions will make this D-type casting to a higher precision when you don't want to. That happened on the SciPy library. For example, here the Hilbert function. When I feed that before the patch, 64 float would take 126 milliseconds to process. And after the patch, it's also from 130 milliseconds. But then if I pass float 32 before the patch, it will take 100 milliseconds. And after the patch is 75 milliseconds. This happens because the Hilbert method was doing the casting internally and doing all the computations and memory allocations in float 64 instead of float 32. So we measured a 35% slower execution with CPU with single precision here. And it's now patched and merged to the upstream. And this problem is amplified if your architecture is susceptible to floating point precision performance. So, for example, GPUs, the performance of GPUs on double precision floating points is way lower than single precision and half precision. So the same problem affected cuSignal, and we observed as 87% slower performance. And now it's also patched and merged to the cuSignal library, so you don't need to worry about this anymore. So another thing that I want to talk about is threading with audio. So some SDR drivers, when you are pulling data from the driver, they will do some blocking calls to kernel or lead USB. And that's very bad when you are working on a real-time application with real-time priorities, because your kernel will freak out if we block that for too long, and your application will start to chug and the audio will start to clip. It causes lots of weird problems. And dramatically reduces the time available for processing here. So it's important to never block your audio thread while using this. And a solution that I found is to use a thread for processing, another for audio, and everything synchronized within buffers. So the processing thread will receive the data from the SDR, process it, and put it into the ring buffer, and then the audio thread will pull data from the ring buffer and play back without blocking the audio thread. So also I want to talk about ring buffers. That is a nice thing that is used on other projects. That is a DSP and a DSP program is a chain of discrete functions sharing a common vector. So input, process, and you have an output. The input and the output are different vectors, and sometimes these vectors have different lengths, and you need to synchronize both of them. So that's why ring buffers are important here. So they provide synchronization between threads. So you can put one producer and one consumer on different threads and synchronize everything, send data back and forth using ring buffers. And also it won't allocate more memory while executing. So it just allocates initial data and then it just reuses it. One thing to keep in mind here is that if your ring buffer overflows, it will rewrite data from your memory, and you need to be mindful on how to use this accordingly, and if all your blocks are working on a real-time fashion. So another important thing here that is more hidden is the stop repeating work. In underlying implementations, for example, the resampled signal of the SciPy signal might duplicate operations. For example, if the if the function this function here, the resample one, will expect a input in the time domain that is the basically block. Now, if the data is frequency domain, for example, you are receiving from your radio and doing an FFT and filtering that, you have a frequency domain data on your hand. And to resample that using this function, you need to convert to time domain. We're using an inverse FFT and then passing to the function, the resample function. But the problem is that when the function receives this data in time domain, it will use a FFT to convert that back to frequency domain. So all your operations here, the IFFT and the FFT, are redundant and it's useless. So because this resample it does their thing in the Fourier domain, so you don't need to ping back and forth from time domain to frequency domain. And this was also but enhanced with this merge, this pull request that was merged. So you can specify which domain that the data input data is. You can choose between time domain and frequency domain now. So if it's frequency domain, it won't do the FFT. If it's time domain, it does the FFT, and you save an inverse FFT and FFT that can cost you a little bit. And so my tip here is that looking at the source code when you are trying to check any better performance is also important. So don't get your code for granted. Mind the methods from third parties. And also, the last point here is that GPU really like frequency domain data. For example, the infinite impulse response IIR filters perform terribly on GPUs because every operation depends on the last operation. So you can't easily parallelize this, and it's a nightmare to run on a GPU. The solution here is to use a finite impulse response for filter to work on the frequency domain. And that way is way easier to parallelize your operations since they don't depend on each other to execute. And GPUs like that. And that's implemented on cuSignal and SciPy Signal using the Frequency-modulated filter and filter. If you are using something that depends on phase, you don't want any phase discrepancies, I would recommend using the filter because it does not have phase zero differences a bit after and before the filtering, so it's easier to work with. So this function here, the FearWin, will you can create like band pass filters, low pass filters, high pass filters very easily. But sometimes you need something more special. The pass band will be something like the FMD emphasis, that is an exponential line according to a frequency. So sometimes you need to use these functions from SciPy Signal to convert your coefficients from IIR filter to a field filter, and this way you can emulate a IIR filter on a FIR-based filter. Here, in the plot below here, we have the fuchsia and the red are exactly the same. So both implementations do the exact same thing, but the difference is that the IIR filter, the FIR filter, is much faster than the IIR. Thank you all for listening. I am available on Twitter, GitHub, anywhere you can talk with me. I really like this topic, and I hope you guys can improve the execution of your applications by this talk. Thank you.
Thanks so much for a really interesting talk. Also, I really like your ham radio call sign.
Thank you.
There. So we have some questions in Slack, and just like a quick reminder, if y'all have questions, please put them in track questions-room-204. From Benjamin Glass, which SDR are you using here?
So I have lots of SDRs.
What's your favorite?
I quite like the simplicity of AirSpy. They are AirSpy R2. They have 10 megahertz of receiving band. It uses USB 2.0, so it's simpler and cheaper. I think that's a good way to start. If you want something extra cheap, I would recommend the RTL SDR. That is $35 and gives you 2.5 megahertz, and it's quite useful for getting started.
Cool. And the next question, also from Benjamin. When you store the data from the SDR, are you storing raw samples or only the demodulated audio? And what data formats are you using?
Yeah, you can store whatever you want. If you want the raw voltages, you can put that into your disk. If you want just the audio, you can just save the float32 audio output on your disk. You can also encode with MP3 or OGG, depending on your applications, or just compressing it with a Python function. But yeah, it will depend on the end application for this.
Cool. And the next question is from Nadigan. What tooling or feature improvements are needed or are on your wish list to make Python better at signal processing?
Better threading. That's something that always gets in Python with real time, but I think we are getting there in a thread-wise thing. And also a good implementation, maybe a standard implementation of a ring buffer would also be good. We have the DQ application, but I think that can be improved with Numpy.
This is another nice opportunity to point out that we have sprints this weekend for anybody who's interested in taking on some of these challenges. The next question is, what have been your favorite resources for this type of data processing in Python? Both like online resources like message boards or like books?
The Python community is flooded with good examples of how to do DSP with Python. I think if you search for SDR in Python, you will have lots of results. There is one blog that will explain like digital demodulation, for example, satellites and stuff, like using phase shift keying demodulation. And that's very interesting. You can basically decode a satellite with your with Python, and your SDR in your backyard is quite interesting. Lots of resources there.
Cool. And then I guess my last question is for me. What about Python makes, or what about like the DSP and this work is like fun to do in Python? Like what makes it worth it doing it in this tech stack?
Sorry?
Like why are you using Python?
I'm using Python because it's very hackable and everyone understands it. So it's quite fun to explain how DSP works. That is lots of math involved on like Python that everyone is like can code in Python is very and Numpy offers like such a wide range of pre-made functions that you can also use that. And to add GPU acceleration, you just change a header and there you are. You have cuSignal handling the SciPy signal and CuPy handling the Numpy, and all of a sudden your code is running on the GPU very fast.
Excellent. Let's see. I think we can, yeah. So I think we can end here. Thank you so much for your presentation. We'll start again at 3 with our next talk in the general session.